Hello everyone, my name is Alfonso Perez-Carrillo and I welcome you all to this course on digital audio coding that I'm teaching at the Engineering Department of the University Pompeu Fabra in Barcelona. This image captures the main idea of the course. So we have an audio signal that weighs a lot and the objective is to reduce its size to a much smaller file that contains the same original signal. We're all familiar with audio codecs, especially MP3, but there are many others: FLAC, AAC, Orbis, Opus, to mention some. So why should we care about audio codecs? Well, we may be interested in storing a song for later replay. We may want to transmit or broadcast at distance, for example, a telephone call or a podcasting internet. And in both cases, we have two parts. First, we have the encoder, which produces a binary code from a source signal. Then we have a decoder that reads the binary code and reconstructs the original signal. And why digital? If we can use analog representations for storage and transmission. For example, we have the vinyl, the cassette, or radio waves. Well, as you may intuitively think, there are many advantages of using digital versus analog. So for example, storage is easier, there is less degradation in the signal, it allows for encrypting, multiplexing in time and frequency, we can regenerate the source signal, we can have an error protection, and we can use many DSP techniques. So we have many codecs available. Which one should we use? Well, it depends on the specific type of application. So some codecs are designed for storage and some for transmission. Some applications need real-time transmission, so think about a phone call or musicians doing a live jam, whereas others can be delayed, so for example music streaming or storing music. For some applications, it may not be very important if we remove some information, but for others, the main restriction is the quality. And also, we may prefer open source to proprietary codecs. So, sometimes it's difficult to say which codec is better than others. Many times it depends on the application. However, in the case of the same type of application, we do have specific measures to compare them. So for example, we have the compression rate, the quality of the sound, the complexity, or the delay to cite some. So now, let's see an example called PCM or pulse code modulation. PCM is not a coding scheme, but a method used to digitally represent sampled analog signals. So we go from analog to digital, and it has 3 steps: sampling, quantization, and coding itself. So we are going to show this graphically. Here we can see the amplitude of a signal over time. So the first step, we get the amplitude of the analog signal regularly at uniform intervals. Each sample is quantized to the nearest value within a range of digital steps. And finally, we get this quantized signal in green that takes the values, for example, voltage, of the middle of the interval. Finally, the third process is the coding itself, which consists of assigning a binary code to each digital step. So, PCM is the standard form of digital audio in computers, and it's used in many applications. In this table, we can see at each column an example application where PCM is used, and in the rows, we show the parameters for sampling and quantization. And what's very interesting is observing how different applications adapt those parameters to their specific needs. So on one extreme, at the left, we have the DVD, and at the other extreme, to the right, we have speech communication. So the DVD uses a very high sampling rate and high number of quantization bits, actually higher than what is necessary for a perfect listening. But this may be interesting when dealing with applications such as audio editing or processing, because this oversampling will allow for a high quality time stretch, which is something similar to a zoom in an image. On the other extreme, we have speech communication, which in fact is removing most part of the information so that the compression rate is very high. Why can we do this? Well, because in a phone call we need real-time communication, so we may be restricted by the bandwidth, and therefore we need a low bitrate so we can compromise quality as long as the listener can understand the message. So in this previous schema, we're mainly concerned with the coding block itself, but actually the other two blocks do also contribute towards the compression, as we saw in the previous slide. In fact, the quantization block is very important to get higher compression rates, as we will see in later videos. The coding block as it's here can actually be applied to any sequence of data. So for example, we can encode zip files, but we're working with audio, so we can take advantage of its properties. So audio can be regarded as a time sequence, and therefore we can use this procedure, but audio can also be seen as two-dimensional with time and frequency, so things get more fun, but also more complicated. So this diagram fits much better to the contents of this course, and it works as follows. So in general, we start with, we separate the contents of each audio frame in frequency bands, either using transforms like Fourier or filter banks. Then, for each frame, we perform the quantization and coding steps, which are actually controlled by a psychoacoustic model. And finally, we save the frame or send it to the decoder that will perform the inverse process. So, this course will be structured following these three main blocks. So block 1 is quantization and entropy coding, block 2 filter banks and frequency transforms, and finally psychoacoustic models. So I hope you like it and see you in the next video.